Okay, thank you everyone. For the next talk in this session, we have Joao Basso, who's going to be talking about optimizing random local Hamiltonians.
Thanks. Yeah, thanks for the introduction. I'm going to tell you about work with great collaborators, Anthony, who's with us this week, and also Alex. And this is about optimizing random Hamiltonians. So I'll start by talking a little bit about Gibbs sampling again. I've already heard about this in the talk before, also the tutorial on Saturday. So I'll just remind you what a Gibbs distribution is. So suppose you have some set of events and you assign energies to them. You say a probability distribution is a Gibbs distribution if the probabilities are given by Boltzmann weights, which is the exponential of minus the energy divided by the temperature. This type of distribution appears in many fields. For example, in physics, when systems thermalize, they end up in this distribution. There's also, has applications in machine learning, statistical inference, and the application that we're going to care about today is in optimization. To see the connection to optimization, you can just see what happens as you vary the temperature. So if you take T to be very large, the Boltzmann weight approaches 1, and this is like a uniform distribution. But as you start to decrease the temperature, this probability distribution starts to concentrate about low energy events. So if you're able to sample from this Gibbs distribution at low temperature, well, you're preparing low energy events. And for now, I'm only talking in the classical world, and some techniques for this type of problem, for example, Markov chain Monte Carlo, for sampling from distributions. But now we want to do this in a quantum world. And first of all, the problem we're trying to optimize is to actually find low energy states of some Hamiltonian that is in general non-commuting. In this case, the Gibbs state as an operator is the exponential of minus h divided by the temperature. And again, as you decrease the temperature, this state concentrates around low energy states. So if we take inspiration from the classical world, now we could think if we're able to do sampling from the Gibbs distribution, maybe we'll be able to optimize quantum Hamiltonians. Incidentally, there has been a recent line of work that has been able to construct efficiently implementable quantum algorithms that can do quantum Gibbs sampling. We heard all about this on Saturday by Cambyse. So a natural question that was already hinted at, the people at the audience were already asking is, now that we can do quantum Gibbs sampling on quantum computers, can we use these algorithms to do quantum optimization? It's a very natural question, and this is what we address. So first, let me mention, in the field of quantum optimization, here's one of the dreams. If we could come up with a family of problems, say a family of Hamiltonians, whose low energy states can be prepared efficiently with a quantum computer, and that you could prove that you cannot prepare them with a classical computer, well, that would be great, right? There'd be a form of quantum advantage. But as you can imagine, it's very hard to achieve all these three things, like to find the right family of problems to look at, to find a good quantum algorithm, and also to prove the classical hardness. And to achieve all of these, it's a big balancing act. There's many things you need to take into account. For one, you need to pick which quantum algorithm you're going to analyze. And like I said, we're going to take inspiration from this line of work of quantum Gibbs samplers. Well, those algorithms are quite complicated, and there's very few guarantees of convergence, mixing time bounds. So what we're going to do is simplify that algorithm. But we need to be careful because there's a trade-off, right? We need to simplify it enough that we're able to analyze it. But we cannot simplify so much that we trivialize the algorithm, and then it's not doing anything interesting anymore. So there's a trade-off we have. Another balancing that we need to do is when we choose which family of models we want to optimize. So we want these models to be easy enough for us to analyze and prove theorems about it, easy enough for the quantum computer to be able to solve it. But at the same time, we want them to be complex enough that they're classically hard and that they're even interesting in the first place. So there's all these trade-offs we need to find, and one of the successes of our work is to find regimes in which we can achieve all these things or almost all these things. So first I'll say the main result informally, and then we'll work our way to the full-fledged result. So informally, we have this theorem that there is a simplified version of quantum Gibbs sampling that is able to prepare low energy states of some family of Hamiltonians. And I'll define how low and what the family is very soon. And once we couple this with existing results on circular bounds, we can see that preparing the same states that our algorithm prepares requires circuits with very large depth, and hence they are classically non-trivial to achieve. So I'm going to right away tell you what the algorithm is. It's very simple to state. So we start with the maximum mix state, and then we do time evolution under some Lin blotting. And we heard all about Lindbladians. You can think about them as a generator of a continuous time Markov chain. They're like a Laplacian. We already heard about them. They have this certain form. They depend on these operators K. They're sort of Krauss operators. And now in designing the algorithm, our job is to pick the correct case. So again, taking inspiration from the classical sampling algorithms, a lot of times you do these local updates, maybe you do bit flips. In our case, we're going to choose our set of jump operators to be single qubit XYZ Paulis. And then for each one of these jumps, we're going to have a Lindblad operator, that is the jump, plus some coefficient y times the commutator of A and H. And that's the entire algorithm. It's an ansatz. If you have a quantum computer, you can run it. Maybe it's good, maybe it's not. But that's our proposal. And like I said, we didn't pull this out of thin air. This is totally inspired by the algorithms that people have found out for Gibbs sampling. And so let me show you how we can arrive at this from their algorithm. So for one, they have a coherent evolution part in the Lindbladian. We already threw that away. And here's what their Lindblad operators look like. So they're a lot more complicated. They have some weight function. They are a filtered version of some Fourier transform of the jumps. It's too complicated. So we're going to Taylor expand these exponentials and only keep up to first order in the commutator. So truncate everything else. We end up with a prefactor multiplying the commutator, and we're going to forget its form. Just call it some constant y that we're going to choose later. And that's how we end up with the Lindblad operators that I wrote down. Okay, so that's our algorithm. Now let me tell you about the models that we consider. And again, in picking the models, we take inspiration from classical optimization. So there are these models called the spin-glass models that were introduced around the 70s to introduce many-body physics, to study many-body physics, for example, of spins in a lattice. And these models are quite interesting because on one hand, they are simple enough that you can state them and you can do computations with them to some extent. But at the same time, they retain enough complexity that they have key features of interesting physical systems. So they have many local minima, they are highly frustrated, they exhibit phase transitions. And there has been a lot of algorithmic development that was done by studying algorithms on these problems. For example, message passing algorithms. A lot of advancements were made by analyzing them on spin glasses. More closer to the quantum community, the QAOA, this other optimization on SATs. It's very hard to analyze, but once people were able to do it on quantum spin glasses, that led to tools that allowed to analysis on other problems, and even analysis of other quantum algorithms. So there's this repeated history of analyzing algorithms on quantum spin glasses, leading to algorithm discovery for other things. So taking inspiration from that, we're going to consider a quantum analog of spin glasses. So first, let me show you what a classical spin glass looks like. This is a canonical one that we see. It's called the Cherrington-Kirkpatrick model. So suppose you have n bits, z1 through zn. The Hamiltonian is defined as the sum of every possible two-body term. And in front of each one, you put a Gaussian random variable. Now, we're going to define a completely analog to this in a quantum setting. Instead of the ZZs, now we're going to have Pauli operators. So we're going to have X, Y, Z, because we want it to be non-commuting. So now you can picture picking every Pauli operator that is supported on 2 qubits. And in front of each one of them, you put some Gaussian coefficient. It's a very natural generalization of the Cherrington-Kirkpatrick model. And we can be even more general and allow the model to be k-local instead of 2-local. And even we can allow the locality to grow with system size. This is not often the case in physics. And a lot of times we consider 2 local models, 4 local models, always a constant. But in our case, we can actually allow for the locality to grow with system size. Additionally, we can also allow for a fermionic version of this model. So now instead of having Pauli operators, we could have Majorana operators that are supported on k sites. As you can see, these 2 models I wrote down, they are supported on dense hypergraphs. Every possible clause is present with high probability. But we can also allow for a sparsification, where you pick a number of terms m, and you just sample m of the possible terms. So this class of problems is quite comprehensive. We can allow for Pauli or fermionic Hamiltonians. The locality can be anything, even grow system size. And the interaction graph could be dense, sparse, or anything in between. It also includes interesting models in physics. For example, the SYK model is included here, the Gaussian unitary ensemble. So it's a quite nice family that we're going to consider, and everything I'll say now will be about this family. And now we can formally define what the goal is. So we want to find a quantum state, which on average, once you measure the energy, it is at least a constant fraction approximation of the best energy, which here I write as the operator norm. And this ratio multiplying the expected operator norm, this is what I call the approximation ratio. And we want it to be a constant ratio, but like I said, since now we're going to allow k to grow with n, we're going to try to pinpoint how this ratio depends on k. And aside, I should note, I've been exchanging minimizing and maximizing without any care. And they're the same up to a sign flip. But the equations I write, we're maximizing, but I might use language that implies minimizing. So let me tell you a bit about what is known about these models. So if you're in the spin case, if you allow nearly linear locality, there's a very good quantum algorithm for it. Now, in the random poly case, if you allow, in fact, you can find product states. They're very good approximations to the true ground state energy. But if you pin down the dependency on the locality, it goes down exponentially. Similarly, there are algorithms, for example, for the SYK model that is fermionic. And again, the dependency in the locality decays exponentially. You're able to get a 1/a poly k approximation ratio if you assume that the graph has bounded interaction degree. So where our work fits in is that we don't need to assume anything about the degree of the graph. It can be fermionic, it can be spin, any locality, and we get a 1/k approximation ratio. So here's the formal version of the theorem. If we simulate the Lindbladian that I defined in the beginning, from the max limit state for a time that goes as 1 over the locality, there's some appropriate choice of y, such that the expected energy you get is a 1/k approximation of the best. Based on the previous works I mentioned, this gives an exponential improvement on the locality. And this shows that our algorithm is pretty powerful in the sense that it is a one-size-fits-all. It couldn't work on the spin, the fermionic, small locality, large locality, dense graph, sparse graph. An algorithm doesn't care. It does the same constant approximation ratio for all of them. And one way to think about the algorithm is the following. So the original Gibbs sampler. If you run it for enough time, you'll get to the Gibbs state. Now, our algorithm, we truncated a bunch. We throw away terms. Quantum detail balance is out of the window. So at long times, who knows what it's doing? But if you run it for just the right amount of time, there's a sweet spot in T where it moves enough away from the max limit state, but doesn't diverge enough from the original algorithm to do something interesting. As a counterpart to that, we can import circular bounds for the systems that show that any other circuit that is able to achieve the energy that our algorithm does, the circuit needs to have a large circuit size. So it needs to be a deep circuit. And then this implies that the states we're preparing, they're highly entangled. And this is indication that we are preparing a non-trivial state, a highly entangled state. Of course, there's no proof of advantage, because we're not proving this is impossible classically, but it is some indication of that. So if you go back to that dream that I put in the beginning, we almost achieved 2.5 out of 3 things. We found a good family, we gave a good algorithm, and we were not able to prove that this is classically hard to do, but we gave strong evidence for it. And with the few minutes I have, I'd like to sketch the proof of the theorem and needed some interesting technical ideas. So this is what we're trying to compute, the expected energy. And what we're going to do is expand to second order in T. The 0th order term is 0. The first is easy to compute. And all the hardness of doing what we're doing is dealing with the second term that we need to balance. So again, we're balancing this T and T squared terms. And 80% of the paper was just dealing with the second term. So this is what we want to bound. And the strategy we found was the following. First, we symmetrized the Hamiltonian by introducing these Hadamakers, plus minus 1 random variables. multiplying each clause of the Hamiltonian. And this is nice because if you square them, they're equal to 1, right? So they disappear. And if you look where they appear in the second term, they appear upstairs in the exponential through the Lindbladian, and also downstairs. So here's our strategy. We'll try to bring the Hademakers from the exponential downstairs, so they pair up and they cancel. And when that happens, the term will have a good bound. We do that through the following identity that says when you have the exponential of a sum of operators, you can bring one of them down. And the price that you pay is this more complicated integral. This is sort of integration by parts. So here's an illustration. Suppose you have a Hadamard multiplying an integral. You use this identity. You bring S1 down. S1 squared. It's 1. It disappears. The term is good to be bounded. Issue is once you bring down S1, you might bring down, for example, S2 and S3. So it seems like you didn't make progress because now you have more variables downstairs, except that these new integrals will be higher order in T. So now you can just recurse. And that's the, I know I'm being a little vague, but that's the idea of the proof. So you keep recursing, and every time you have Hademakers, you keep expanding. And now the whole point of the proof is to be able to keep track of all the terms, bound them, and show that the sum converges. To do this, one way you can do is to keep track of all the Hademakers that appears. And you can, with a more complicated example, you can see that the Hademakers that are appearing, they form sorts of paths that links indices of the Hamiltonians. And then all you need to do now is to be able to count and enumerate all these paths. And we develop this sort of diagrammatic calculus to keep track of all the terms that appear. And this is how we bounded the second term. And you know, I know that was quick, but I just wanted to give a little flavor of what the proof looks like. And to finish up, let me mention some open questions. So with the normalization that we have for our problems, you know, I've been writing operator norm. You can see that it's always upper bounded by root n. The previous algorithms were able to get root n divided by exponential of k, and then we improved this to root n divided by k. Now there's this question: well, what is the true best energy? You know, for one, this is you can think about it as just a probabilistic question. You have a random matrix. What is the largest eigenvalue? If it's actually not root n over k, and we're not optimal, if it's root n, for example, then there's another computational question, which is now, what is the algorithm that is able to find this energy? Another question is about this classical hardness, right? We just only give indication, we don't really prove it. So either proving it, or in fact, you know, there's many people that are very good with classical simulation and have your classical ansatz. I invite you, if you're able to find the same approximation ratio, that would be very interesting. Also, this is a new algorithmic proposal. Now, there's a new ansatz. You can run it on whatever you want. Pick your favorite problem. Maybe the algorithm is good. Maybe it's not. You could try and see what this algorithm does for whatever problem. And if you're interested in this, you know, I've been thinking a lot about this, so I'd be happy to talk more about it. And also, you can think about other generalizations of our ansatz. So when we came up with this algorithm, there is a lot of choices we made to simplify the original Gibbs sampler. There's many other things you could have done that could yield more powerful or maybe less powerful algorithms. So there's a lot there to find, and in general, to find out if you can use quantum Gibbs samplers to optimize random Hamiltonians, or even non-random. And with that, thank you so much for your attention.
Hi, I guess one quick question. So for the pages, we have the diagram. How to interpret the diagram?
Oh, yeah, I was very vague about this, and I didn't intend to actually explain it in detail. But so every time you bring down these Hademakers, they start to pair up. In this diagram, every node of the graph represents a term of the Hamiltonian. And every time you form a line that has the same index on both ends, the line stops expanding because it means you paired up all the terms. Whenever this happens, you're able to bound the term. If the path hasn't ended yet, then you keep expanding.
Hi. Yeah, so I have a question about the sort of the classical limit of this.
Mm-hmm.
So if you choose your Hamiltonians to be only from Z strings, only ZZ Hamiltonians,
Mm-hmm.
and suppose you also cleverly choose your jump operators. Does this imply that there is a classical Markov chain sampler that is like good at finding, at solving like classical constraint optimization problems?
Can you say the last part again?
Does it imply that there is a classical Markov sampler that is good at finding solutions of classical constraint optimization problems, like classical spin glass problems?
Right. Yeah, I don't see how that directly implies that. Our results are only for these, very nice, random, symmetric, non-commuting Hamiltonians.
I see. So
yeah, I don't know what this says about a classical CSP.
okay.
Yeah. Although, sorry, I'll add to that. But nothing stops us from running the algorithm on SCSP, and maybe could do well, maybe could. I think it's a nice thing to try.
Yeah, does your algorithm analysis tell you how to choose this evolution time, and how does it scale?
Right. Maybe I went too fast. So yeah, here in the, so we're able to compute exactly what this tunable parameter y is supposed to be, and also what the time is supposed to be. So the time goes as 1 over k, the locality.
Okay, thanks. Is it possible that the errors are somehow better behaved, and if you account for all the errors, the actual optimal time is different?
I don't know. Yeah, this is all very asymptotic. Yeah.
Okay, thanks.
Thanks for the talk. My question is, you introduced this quantum spin glass model. I am wondering, is there any concentration type in result for the ground state, or because you have a random, you have a random Hamiltonian, right?
Right.
And your ground state is also random. Is there any concentration property for this?
Right. So we heard about, for example, Robbie's talk. I don't know if you're there. So generally for these models, all these circular bounds, they come from concentration properties. So the circular bounds work because for any fixed state, there's very high concentration.
Thanks.
So you said you were inspired by classical spin glasses when you were coming up with your Hamiltonian, and also that the ground states end up being very highly entangled. So is this at all related to the topological spin glasses? Or do you know if this is an example of that, or?
I'm not sure. I think Anthony would be better to answer that. Anthony, if you want to say anything. Yeah, I don't know either. Yeah.
Are there any more questions?
Hello. Yeah. Thanks for the nice talk. Yeah, in the back of the room. Do you have any intuition on what would be the any specific class of family of Hamiltonians, not random Hamiltonians, for which your algorithm might do very well compared to other existing methods currently?
I don't have any intuition. This is the only family where we have done a thorough analysis beginning to end. For other models, the computation is not as nice.
Thank you.
Yeah, I think the first way to try to answer that is just run numerics and see if it does well. But a lot of the proofs we have only work because we have these random models that have a lot of symmetry.
Okay. Thank you.
Any final questions? Okay, so if we thank Joe again.
Thank you.